We'll begin the afternoon session with Abhijit Gadde from TIFR. He'll be telling us why holographic states are special.
Okay. Let me start by thanking the organizers of the workshop for inviting me and asking me to present my recent work. So, as the title suggests, I'll be talking about what makes holographic states special. I'll first say, what I mean by holographic states, and then I will say, what do I mean by them being special. So this is a work that we have been doing in collaboration with Jonathan Harper, who is in the audience, and you will hear his talk on Friday, and Vineet, my student. This also includes some of the past work that I did with some of my students, Shreyans, Rakshu, and one of the undergrads, Harshal. Okay, so let me just elaborate on the question a little bit. What do I mean by a holographic state? So first of all, we have a CFT with a large central charge and large gap in the spectrum, and conjecturally it is dual to a gravitational theory, one higher dimensional gravitational theory. And by holographic state, I mean a state in such a CFT that is described by a classical bulk geometry. For example, you can think of a canonical example as the vacuum state in 2D CFT, 2D holographic CFT. In fact, this is the state that we'll be working with during the most of my talk. Although the ideas are general and can be applied to either other states, other holographic states in 2D CFT, such as a thermophilia double state, or states in higher dimensional CFTs as well. Okay, so we have this state in 2D CFT, which has been prepared by a path integral on a hemisphere, and the state lives on the equatorial circle. And we divide this spatial slice into 3 regions. Here I've denoted them as A, B, C. And according to this decomposition, the Hilbert space of the theory living on the circle factorizes into the Hilbert space associated to region A, B, and C. And in this way, this state can be thought of as a multipartite state. And we'll be interested in characterizing this multipartite state, or at least we would be wanting to say as many things as we can about this multipartite state up to local unitary transformations. We are not really, because we can change the basis and get a different presentation of the state locally. So we will only be interested in characterizing this state up to local unitary transformations. So this is what I mean by holographic state, and this is its Hilbert space decomposition. Okay, so the question we are asking is that this multipartite state, does it have any special properties compared to a generic multipartite quantum state? Now we know one answer to this question. We know that if two parties, two regions which are sufficiently small, if they're sufficiently small, then their mutual information vanishes. Okay, and this follows from the Takayanagi formula. It appeared in several talks in the morning also. So if you compute the entanglement entropy of A union B, it is just the sum of the entanglement entropy of A, the individual regions A and B. So in particular, the mutual information between A and B vanishes. So this is something that you can say about the state, because you have this geometric handle at your disposal, because the entropy is given geometrically by these minimal surfaces. A priori, even to say this, it would have been a non-trivial statement. I mean, it is a non-trivial statement. Also, one thing to notice is that even though this condition that the state obeys is just a number worth of condition, I in general is a positive number, and when I is equal to 0, it doesn't mean that the state lives in some codimension 1 space, but rather it's a dramatic condition on the density matrix. It says that the density matrix of A and B, obtained by tracing over C, let's say, is factorized into the density matrix of A and B. So already we can see that such a simple condition has dramatic consequences on the structure of the state. Now what else can we say about a multipartite state? This is a characterization that was possible just by thinking about them as bipartite states. But if you think of them as multipartite states, can we say something more? Now, as I said, to be able to say this, an important tool that allowed us to say this is the Takayanagi formula, which geometrizes the entanglement in the state as areas of minimal surfaces. So one can exploit this and study the geometry of minimal surfaces and get inequalities that are obeyed by these areas, and those will be the inequalities obeyed by various entanglement entropies. And this program, it goes under the name of holographic entropy cone. We'll hear more about it from Bartek later on. But just a couple of points about this. So what we get out of this program are inequalities, which is quite impressive and interesting, although they don't necessarily lead to a reduction in the dimension of the subspace in which the state lives. Something that is the result of such equalities. And also, these inequalities are constructed out of entanglement entropies, which are measures of bipartite entanglement. Now, one can compute one can have a multipartite state and compute entanglement with respect to any bipartition and take its sums and products, but at the end of the day, it's still a bipartite measure. So let me elaborate on this point a little bit. So for multipartite states, we can construct entanglement measures using entanglement entropies of various parties and their unions and their combinations. So the mutual information that we saw is just the addition of A and B minus entropy of S, A union B. Similarly, there's a triple information that people talk about, which is this combination. So these quantities can certainly be quite useful, but because they are constructed from density matrices, they are bipartite in nature. So just to appreciate this point a little better, consider these two states. Now, these two states, it turns out, are not equivalent to each other up to local unitary transformations. Although if you construct any density matrix from these states, they have the same spectrum. And this was a very simple example with 3 parties. 3 qubits, but you can construct complicated examples also with multiple parties and the dimension of each party also being large, with the property that their density matrices, all of their density matrices have the same spectrum. So no quantity such as entanglement entropy or any entropy which is constructed out of a density matrix can distinguish these states. So just to distinguish these states, we have to construct measures which are genuinely multipartite in nature. So as I said, the previous quantities, these quantities, they are constructed from a density matrix, which is defined with respect to bipartition of parties. Even though you have multipartite state, in order to construct density matrix, you first make a bipartition between these parties and trace out one part and consider the matrix and the other part. So it is really a bipartite quantity. So that's why the invariants that you compute from the density matrix are bipartite in nature. The key to construct multipartite invariance is to use the full tensorial structure of the state. So just to give you an example, consider this state psi, and I have denoted its indices with respect to each parties as I, j, and k. And you can construct this combination, for example, where you can see that the J1, K1 is contracted here, and J2, K2 is contracted here, and so on. So basically, I've traced out this party B and C to construct a density matrix A, and then I've taken 3 copies of that. So it essentially is trace rho A to the rho A cube. However, with the same number of psis, so 3 psis and 3 psi bars, you can construct this quantity, where the indices have been contracted in a different fashion. And the point is that this quantity cannot be written in terms of a matrix. It cannot be written as a trace of any matrix. In that sense, this would be a multipartite invariant. And in fact, if you compute this for these 2 states, you will see you will get different answers. And that's how you know that they are inequivalent up to local transformations. Okay. Now, the key to construct invariance, local unitary invariance, is to contract indices. And these index contractions can be cumbersome. So in order to construct multipartite measures, it is convenient to develop a graphical language for index contractions. Now, one comment, when I say multipartite measures, this word measures, multipartite entanglement measures, is a little loaded word. it can mean different things for different people. So for quantum information theory people, you would, in addition to them being invariant under local unit transformations, you would also want them to be monotonic under what is called local operation classical communications. So we will not be considering that aspect of these quantities, but we will just focus on them being invariant under local unit transformations. I mean, one can ask these questions. We have a paper, not a different paper, where we have investigated this question and constructed families of multipartite invariants that are LOCC monotones, but that will not necessarily play a big role in the discussion that we will have here.
Also, you won't impose that they vanish for separable states, right?
Yeah. Yeah, so that's all this LOCC monotone discussion. If you have those, then they will vanish for separable states. Yeah. Yeah. I mean, it will take a little bit afar into that discussion, but the idea is to construct them for pure states first and to define them on mixed states as what is called the convex roof construction. And what we have are the quantities for pure states. So if you define them using the convex roof construction, it will obey this property. Yeah. Oh, just because you have contracted all the indices. So when you contract indices, so if you transform this guy, it will transform as a tri-fundamental. I mean, it will transform under a unitary of party A. So I1 is a fundamental index with respect to party A. J1 is a fundamental index with respect to party B. And K1 is a fundamental index with respect to party C. So because you have contracted I1 here with, let's say, I1 here, so this transforms in an anti-fundamental way. So when you transform by unitary matrix, you will get a U here and U dagger here, and contraction of indices will cancel the U and U dagger. And as long as you keep, contract all the indices, keep no index dangling, you will be constructing a invariant under local unitary. Okay, good. So now graphical language for this index contraction can be developed straightforwardly. So here we have a psi with 3 indices.
Abhijit.
Yeah.
So this statement which you wrote down in the last, that any graph which is not necklace is multipartite. Is it generally true? I mean, for more than 3 legs, if going from a node, let's say if you have more indices, I1 to Ik, then also it's true or more?
Yeah. So you have you're representing psi as a white vertex, let's say, with 3 edges coming out of it, and the 3 edges describing the 3 indices corresponding to, let's say, party A, party B, and party C. Similarly, you have a psi bar, the conjugate, and it has also 3 indices, but they transform in an anti-fundamental way with respect to the local unitaries. And the contraction of indices simply means that you are joining these 2 edges. So effectively, you are constructing a graph with white and black vertices, a bipartite graph. That's because you can only contract indices of psi and psi bar, not psi and psi. So it will be a bipartite graph, and each vertex will have this 3 colored edges incident on it. So a graph of this property will give rise to an invariant in a unique way. So this quantity that we have written down, you can see this index contraction. This green, the party B and C, they go together. So that's green and red, they go together always. And I1 contracts here like this. So the blue party goes separately. So essentially it gives you, another way to say this is to, if you look at this object here, is just trace row A, because you have traced over B and C, and then you have taken 3 copies of that. So trace row A cube. Okay, so that's why the quantities that you can construct out of density matrices will always look like necklaces. Okay, but of course, you can do much more than that. If you just want to construct graphs, you can just contract indices any which way you want. And in fact, that is the most generic thing to do. So this, when I say multipartite invariant, is not some very carefully constructed quantity, but any generic graph of this kind will not be a necklace and will give rise to something that probes the multipartite nature of the state. Okay, so how can we systematically characterize such graphs or such measures? So this can be described in terms of a permutation tuple. What do I mean by that? So let's take n number of replicas. So here I've taken three replicas. So I have 3 copies of size. 1, 2, 3. I've labeled them 1, 2, 3. And 3 copies of psi bars. 1, 2, 3. And now I want to contract indices. So I have a red index coming out of this. I have to say where it contracts to. I have the red index coming out of this. I have to say where it contracts to, and so on. So effectively, for the red, as a red edge, I have to give a permutation element, which describes how it contracts with the indices of psi bar. Similarly for the blue edge, and similarly for the green edge. So for every party, I have to specify a permutation element in Sn, where n is the number of replicas. So in this particular case, for I2, I have this graph, and the blue, for example, is just the identity permutation, 1, 2, 3. And the green is 1 going to 2, 2 going to 3, 3 going to 1. So it's a cyclic permutation, and this should be red here. Sigma red is this oppositely cyclic permutation. Now, so this shows you that any graph or any measure can be thought of or can be specified by giving a permutation tuple associated to each party. But this is a slightly redundant labeling, because you can take this graph and move these black dots around, and what that corresponds to is it corresponds to the left multiplication, right multiplication of this tuple by a same element. Okay, so this is like a gauge redundancy in this description of the measure. Okay. So once we have this kind of a description of these multipartite invariants, we can see how those can be computed in a quantum field theory. So again, going back to the simplest example of 2D CFT, the vacuum state in 2D CFT, we have, so we take this measure here, we look at how these edges are contracted, and we exactly mimic that on the quantum field theory side in gluing of the regions. So we have, for every white vertex, we have every bra, which is constructed by the path integral southern hemisphere. And for the ket, I have a path integral northern hemispheres. I put them like that. And let's look at the blue. So the blue parties are contracted like that. That means the blue region is just glued to the blue region here. And then the red regions are contracted like this. That means this red region is glued just the way it is specified by these permutations. So from this kind of a graph, there's a very natural map to the manifold path integral on which will give you the multipartite invariant for the quantum field theory. In the 2D case, this will be some Riemann surface of some genus, and that genus can be computed using Riemann-Hurwitz formula, because what you will get is effectively a cover of a sphere, because you started off with a sphere, which will be ramified at the 3 points, and depending on, and using this, using ramification index, meaning how many times you have to go around it to come back to the same point, which is the ramification index. Using that, you can compute the genus of this surface. And in this particular case, the genus of this glued surface is 1. Okay. Okay, so we translated these measures, the computation of the measure, to computation of a path integral on some interesting Riemann surface. Now, to compute this path integral is a difficult task in a general quantum field theory. Depends on the details of the theory in general, but if the theory is holographic, then one can get a universal description. Okay, so the idea is to use the dual description to compute this path integral. Now, the partition function is e to the power minus SB, where SB is the action of the dominant bulk solution B, which fills out this boundary surface that we just constructed. This is some torus, and the dominant bulk solution will be some handle body, which will fill in some cycle, and the action of that would be the partition function in the large n limit. So that's what will give you the measure. Yes?
Do you ever get non-orientable surfaces by this gluing?
No, I don't think so.
Even if you use general permutations and not just the...
Yeah, I think so. Okay. Now, so we simplified this problem to some extent. We simplified this problem to computing the action of the volume of the hyperbolic manifold that fills in this boundary surface. But even that problem is difficult. And in order to handle that, we would like this measure to have some symmetry, and then we would like that symmetry to be respected by the bulk solution so that we can orbifold by it and obtain a relatively simpler description. So to begin with, at 0th order, we want the measure, this kind of a measure, to have a symmetry G, which acts freely and transitively on the replicas. If we do that, then whatever this boundary surface is, we can quotient that boundary surface by G and go back to the original manifold, which is S2. Okay, so the boundary at least can be quotiented by this replica symmetry group G, and we get the description in terms of the original manifold. Now, if the replica symmetry is also enjoyed by the bulk solution, which in general is a non-trivial thing, then we can quotient the bulk solution itself by G. And because the boundary quotiented by G is S2, we get a hyperbolic geometry with S2 as the boundary, with possible conical singularities in the interior. Okay, the conical singularities appear because the action of G on B may have fixed points, and those fixed points will give rise to conical singularities. So this motivates construction of multipartite measures with replica symmetry that acts freely and transitively on the replicas at 0th order. The next order, we have to ensure that this replica symmetry is also enjoyed by the bulk solution. Okay. Now, this first problem is a relatively simpler problem to solve. In fact, it turns out, as I will describe, you can construct measures with any replica symmetry that you want. Okay, and then we will have to worry about whether the bulk solution will also have that replica symmetry or not. Okay, so in particular, this kind of I2 that we have, it does not preserve the replica symmetry. Okay, so let's first talk about this problem of constructing the measures with replica symmetry. And as I said, the non-trivial problem is to analyze whether the replica symmetry is also preserved by the bulk solution. Now let us look at the problem of having replica symmetry action that is free and transitive. So this can be, as I said, can be solved for any group G, and in the following way. So you take the finite group G that you want to have as the replica symmetry and take mod G worth of replicas. Okay, so you're thinking of G as a set now, and you're indexing each replica with that element of the group. And now you assign each party a generator GA of the group. Okay, we specify that this party A index of H bar is contracted with that of GA.H, I mean GA acting on H get. So this is an action of the group on the group by left multiplication. Okay, so this is a somewhat special type of construction where so in general the measures can be described just by assigning any permutation element, but here we are assigning, we are taking this action to be left multiplication by a group. Or here, well, right, left, it should be left multiplication. The advantage of this is that the action of the group on the replicas by left multiplication commutes with the action of the group by right multiplication. And because this right multiplication action commutes, you get a graph which has an automorphism, which is G itself, okay, where the action now is by right multiplication. If you are familiar with the Cayley diagrams, this becomes very easy, because what this gives rise to, the graph that comes out of this construction is what is called the Cayley graph of G, and Cayley graph has automorphisms by the right multiplication.
Is H a number or a group element?
Yeah, so the replicas, yeah, it is a group element, but it is also an index of a replica. Oh. It is labeling a replica. I see. Yeah. Yes, so as I was saying, in this way, a measure with any given replica symmetry can be constructed. So you specify G and a bunch of generators of G assigned to each party, and that will give you a measure with G as a replica symmetry. Okay, so now we will see some examples of measures which do preserve replica symmetry. So as I said, any graph with this appropriate property, it should be a bipartite graph and should have edges of 3 colors incident on it, would give rise to a 3-partite measure. So consider this as a measure. This is basically a 3-dimensional cube attached in this way. These are all blue lines, these are all red lines, and these are all green lines. So this basically gives you some invariant. It requires 4 replicas because of 4 psis and 4 psi bars. Okay. Now, as I said, you can construct boundary surface corresponding to that, and that's a genus 0 surface. You can compute that by Riemann-Hurwitz formula, and the replica symmetry for this measure is Z2 times Z2. Now this genus 0 surface, you can think of it as a cover of the sphere itself with some ramifications, but because it's genus 0, you can while transform away this conical excess and get back to a round sphere, which is what I've denoted here. So here this is a round sphere where this white region corresponds to what was the southern hemisphere of the initial copy, and the gray region corresponds to the northern hemisphere. So you can see that there are 4 southern hemispheres and 4 northern hemispheres isolated together to form this genus 0 surface. Okay, and here the Z2 times Z2 symmetry can be realized as just rotation around the x-axis and y-axis by 180 degrees, and the rotation around z-axis by 180 degrees is just the product of the two. Okay, so that's the replica symmetry Z2 times Z2. Now it's clear what is the bulk geometry that is dual to this. It's just the hyperbolic ball that fills in the sphere. And because the Z2 action is specified so straightforwardly, which is basically this rotation, it is clear that the bulk geometry, namely the 3-dimensional ball, will also preserve it. If you want, you can just slice this layer by layer into spheres, and each layer you will have this action. The center is of course important, where there is a fixed point of all the Z2s. Okay. Another example of this, now a 4-parted example, is this one, which is a 4-dimensional cube. Okay. The surface corresponding to this is a genus 1 surface, a torus, and I have given this tessellation of the torus here. I couldn't quite draw this nice 3-dimensional figure, so I resorted to more mundane methods. So I have this description of the torus, and you can see it's tessellated by 4 northern hemispheres and 4 southern hemispheres. And the replica symmetry here is Z2 times Z2 times Z2. Now here it's not so clear, partly because I couldn't draw the 3D thing, that the bulk, which is a handle body, which fills in the torus, obeys the Z2 times Z2 times Z2 replica symmetry, but it does. Okay. So even here, the bulk solution respects the replica symmetry, which is Z2 times Z2 times Z2. So what we will do now is we will mod out by this replica symmetry. Okay. The reason to do that is that the boundary ends up being the nice S2 that we started off with. So here, when we mod out by Z2 times Z2, we get a sphere with 3 conical singularities meeting at the center like so. And these conical singularities are with cone angle pi. Okay, that's because you can see that this sphere, the action was fixing this x-axis, y-axis, and z-axis. And when you mod it out, all these and this z, x, y, z axis meet at the origin, and this is their intersection point here. So effectively, when you mod out by these z2 times z2, you get this kind of a orbifold, where you have a sphere on the boundary and 3 conical singularities with cone angle pi meeting at the middle like this. Okay. Now even more difficult to see is this orbifold, where you orbifold the torus by z2 times z2 times z2, and you end up with this picture, where you have these singular loci starting from these the separating points of the regions. They shoot off in the middle, and so this you can basically see by some local analysis, that there have to be some conical locus shooting into the middle, into the bulk, with cone angle pi here, pi here, pi here, and then something must happen in the middle. And the thing that happens is that they meet up, form another singular locus with cone angle pi, which splits into these two. Okay.
Why is the second diagram inside a sphere?
Oh, because as we said, that because you started off with the sphere, quotienting that, the boundary goes back to the original boundary, which was the sphere. Yeah, torus, this is the torus, but now we are modding the torus out. In fact, we're modding the entire handle body out. So torus filled in with the hyperbolic geometry, we are modding that out. So in particular, the boundary torus goes to the sphere, and what happens in the bulk is a little non-trivial, but this is what happens. It develops these conical singularities, which have this kind of picture. And depending on the cross ratios, you might get the S channel or you might get the T channel looking picture. Okay, good. Now here we described this explicitly these 3-party and 4-party measures, E3 and E4, but this can be generalized to Q parties. You simply look at the Q-dimensional hypercube with Q colored edges. And it so happens that it continues to obey replica symmetry in the bulk. So the genus corresponding to the boundary surface would be higher, now 3, 4, and so, I mean one can explicitly write it down as a function of Q. I haven't done that, but it increases. So you get higher genus surfaces. So the bulk solutions that fills them out would be some higher dimensional, higher genus handle bodies. But the non-trivial point is that the replica symmetry is preserved, and you get, after modding out, a picture of this sort. So here I've described a dual, thank you, a dual with 5 regions, a dual of the measure with 5 parties, A, B, C, D, E, and you again get a trivalent graph where each edge of the graph is a singular locus with angle pi. And this graph has Q leaves, which ends like that. So this is the general picture that you get for this family of measures. Another condition on this, so here note that I have taken all the regions to be distinct. So with 4 regions, I'm thinking of them as 4-party. With 5 regions, I'm thinking of them as 5-party. But of course, I could take A and this also A. So even though I have multiple regions, there could be less number of parties. The condition for those graphs is that, so first of all, notice that for every region, there is a chamber in the bulk Cauchy slice, right? And the condition is that if the 2 labels are the same, and if the chambers, then the associated chambers cannot share a wall. There cannot be a wall. This is kind of like the analog of the homology condition in the Takayanagi formula. Okay, fine. So it turns out that the measures that we described, they obey an inequality, which can be proved using a Cauchy-Schwarz inequality for general quantum states. If you take a Q-partite measure, A1, A2, Q parties, and compare it with a Q-1 partite measure, where you have identified 2 parties as 1 party. So A and B, I'm now thinking of as 1 party, and now I'm computing a Q-1 partite measure. So that is necessarily smaller than the Q-partite measure. This you can show using the Cauchy-Schwarz inequality. So what does that mean for these bulk solutions? So consider this geometry that computes E4 for us with regions A, B, C, D. And this other geometry where we have identified B and C and thinking of them as the same party, there, as we said, there cannot be a wall in the middle, right? So we have to pop this wall, and as a result, these 2 singularities, they kind of do this. And keep in mind that these are heavy singularities. They have cone angle pi, so not very light singularities like the RT surfaces, but heavy singularities. So, the geometries, even though they look simpler, kind of non-trivial. But topologically, it's clear what is happening, that this conical single locus is just ending here and here. So this is the action corresponding to this is the E3, okay? And this Cauchy-Schwarz inequality is telling us this inequality between these actions associated with these conical manifolds, that the action for such a thing is greater than equal to, greater than the action for this. So how do we verify this? So this can indeed be verified by using what is called the Schlafly formula. And the Schlafly formula basically says that the derivative of the action with respect to the cone angle is proportional to the area of this singular surface. Okay, so you can think of going from here to here by reducing this cone angle pi, or the conical deficit pi, reducing it to 0. Okay, slowly, and at every stage this derivative is positive. So with that, you can establish this inequality. Okay, now we are in the position to answer this question that we started off with. What makes the holographic state special? Well, so we saw from this point of view what happens if you identify C or D. Now let's ask what happens if you identify A and D. Well, when you identify A and D, because there is no wall that they share, you don't have to pop any wall, right? So nothing happens. So the singular locus that you get, or the singular geometry that you get that computes the 3-partite measure E3 associated to A union D and BC, is the same as the geometry that computes this 4-partite measure. Okay, so that means whatever this quantum state is, this 4-partite measure is the same as the 3-partite measure. Now, the way we arrived at this was, somewhat straightforward. Of course, it involves the analysis of replica symmetry and so on. But however, this now leads to a non-trivial statement about the state, that there are 2 multipartite measures which happen to agree on the holographic state, which is very similar to the kind of statement that we had with the vanishing of the mutual information. Right? So this is also kind of a statement which says that some multipartite mutual information between A and D must vanish. Okay, but it's not equivalent to the vanishing of the mutual information. In fact, geometrically also you can see that it's not the same regime in which these two are applicable, because these are singularities with cone angle pi. Okay, so
What leads to this diagram rather than the cross-ratio diagram is the sizes of the region?
yeah, so here I'm taking A and D to be kind of small compared to B and D. Yeah, if you were in the other phase, then identifying BC wouldn't have done anything. So then you would have a different equality. But the point is that you are getting equalities of multipartite measures, and one would have to explore, what that means from a quantum theory, quantum state point of view. Yeah, I think so. Yeah.
I see. So you can find examples where the mutual information vanishes, but so in qubit systems you can construct such states.
You can construct such states. Yeah. In fact, you can characterize what exactly they mean. In this case, in the simpler case. So let me just say that. So vanishing of the mutual information, we saw that a density matrix on AB factorizes into density of A and B. Similarly, this equality means that you can construct an object which is kind of like a density matrix, not quite density, so I should not even use this notation rho, but some matrix M, which is a matrix whose Hilbert spaces are 2 copies of A and 2 copies of D, and they factorize into A prime and D prime. That's what this means. So the rho is a quantity that is quadratic in psi, and this is a quantity that is quartic in psi.
Quick follow-up question. Of course, you could try to impose vanishing of mutual information for all kinds of intervals, not just for 2. And even then you're saying this would be stronger. Like, you could try and impose it for...
Well, I don't know
A
about
and
stronger. I think it's a separate condition.
I see.
Okay. So I gave here some examples of a family of multipartite measures which can, this was a statement about 4 and 3, but of course you can go back and compute this 5-partite thing. And now I think of this as a 4-partite thing where I identify A and E. Again, there are no walls in the middle. So this 5-partite measure is the same as the 4-partite measure where I have identified A and E. Similarly, I could even do, I can keep on doing that. So it will generate more and more equalities for me. But again, this is an example of a certain family of multipartite entanglements, but you can approach this question more systematically and identify class of multipartite invariants which would lead to such equalities. The key is to realize that such equalities are possible if the bulk solution preserves replica symmetry. So this again motivates this question of finding measures which with the property that the bulk geometry preserves replica symmetry. So we can systematically classify these measures, and here in order to realize or classify such measures is to realize the nature of the singular locus that a hyperbolic orbifold can have. So it turns out that the singular locus must form a trivalent graph with each edge representing a singularity with cone angle 2 pi by n. In the previous case, n was 2, but in general, it can have any value, but of course it will subject to some constraints, as I will say. So a priori, hyperbolic orbifold must have this trivalent graph kind of structure where each vertex is a junction of 3 singular loci with the labels n1, n2, n3. Where by these labels I mean the cone angles associated to this. This n1 means the cone angle is 2 pi by n1 and so on. Now if you if you label each edge by these integers, then allowed trivalent vertices are, so these are the only allowed vertices, 2, 2n, 2, 3, 3, 2, 3, 4, and 2, 3, 5. Okay. So previously we were just talking about junctions with 2, 2, 2, where all the edges in question were 2, 2, 2. But in general, such trivalent junctions are possible. And this is not so mysterious. It might look mysterious, but it's not so mysterious if you think about it. Because if you have such a junction, just drill out a ball around it. Okay, and that ball, the boundary of that ball will be a sphere with 3 conical points. And those conical points will have an angular, the angle around them would be 2 pi by n1, 2 pi by n2, and 2 pi by n3. Okay, so in particular, in order to get that neighborhood, you have to start with a sphere and you have to orbifold the sphere by some finite group. Okay, so in particular, that means that the action, the finite group action on the sphere must be part of the isometries of the sphere, which is SO3. So we are interested then in finite subgroups of SO3. And those subgroups, they have been classified from long ago. And these are nothing but the symmetries of regular polytopes. Okay, so for 2, 2, 2, we had this, and 2, 2n, we get this kind of a tessellation. 2, 3, 3, we get this. 2, 3, 4, we get this, and so on. So this follows from the symmetry of a tetrahedron. This follows from the symmetry of cube and octahedron, and this is both of them have the same symmetry, and dodecahedron and icosahedron have the same symmetry. Okay, so the point is that if you take the sphere and orbifold by this symmetric group, you will get, so for example, if you take this and orbifold, you will get a junction with the labels 2, 3, 3, here you will get 2, 3, 4, and so on. Okay, so at least the local structure of the singular locus we characterized here, that if they have a junction, then the junction must have these labels 2, 2, 3, 2, 2, 2, 3, 3, 2, 3, 4, 2, 3, 5. Okay, and now so if you just restrict to that, then that means we classify all the tripartite measures which obey the replica symmetry in the bulk, where the regions are connected. But of course, we can do more. We can construct general partite measures using this by learning how to glue these conical singularities, how to glue these junctions together to get some more interesting structure of conical loci, such as the S-channel looking graph, or even more complicated trees. And the way to do that is to start with the group associated with this, and start with a group associated with this other junction, and do a procedure which amounts to gluing of these conical singularities, and get a group associated to this junction. And such a prescription is basically what is called the group amalgamation. So if you have group G1 and G2, they are amalgamated by identifying a common normal subgroup H. So G1 had some H. So here there's some group. Okay, I think it's what is called the odd part of this symmetry group on 4 letters. So A4 it's called, alternating A4, and it has these normal subgroups Z2, Z2, and Z3, and this is some other complicated group, and it has the normal subgroup Z3, Z5, and Z2. So now take Z3 and Z3 and identify them. So you'd start with a free product of G1 and G2, and then you mod it out by the action of H, which is Z3, and this action is diagonal. It acts on G1, also on G2 together. Okay, and in this way you can get the group associated with this. Now in general, this would be an infinite group, because the free product will give rise to infinite groups. But then you have to learn, you have to impose some further conditions to get a finite group. So as I said, in general, the amalgamation procedure will give an infinite group. We have to further quotient by a normal subgroup that is free to get a finite group. Okay, now this has a very interesting physical consequences. If you start off with this amalgamated group, it has infinitely many free normal subgroups with finite index, meaning after quotienting it gives rise to a finite subgroup. And each choice of these normal subgroups will give rise to different quotient groups. And those quotient groups then will define some measure. Okay, and the point is that they will define different measures, but the singularity structure that you will get by orbifolding by those would be the same. So in this way, you can get an infinite family of measures like a general class of measures which agree for holographic states, giving rise to even more equalities that holographic states must obey. So the previous example of agreement of 3-partite and 4-partite measures can be explained using this general construction. Okay, so this is my last slide. So as we discussed, there are infinitely many multi-partite measures that agree on the holographic state. You simply have to ensure that the bulk solution obeys replica symmetry. In particular, these agree on the, well, this was the example that we have been working with, the vacuum of the 2D holographic CFT. So in the case of 2D, many of these conjectured equalities can be explicitly checked from CFT. So Jonathan will be giving a talk about it on Friday, as I said, and later on in the next week also. Now, what do these equalities mean from a quantum information point of view? Now, it would be interesting if we can take all these equalities and identify unify all these equalities in some single property of the state. And that would definitely improve our understanding of holographic states. And as I said, the entire discussion was on 2D CFT, partly because 3D hyperbolic orbifolds are much more well studied compared to the higher dimensional analogs. However, as we discussed, the key role is played by the junction coming from the symmetries of S2, should have been. But finite subgroup symmetries of higher dimensional spheres are also well known. These are basically higher Coxeter groups. And it is also clear how to amalgamate such groups. So in principle, this construction is possible, except that this is somewhat new mathematical discussion, and one would have to tread carefully. All these other discussion about hyperbolic manifolds, 3D hyperbolic orbifolds, that is somewhat standard description, standard discussion that mathematicians have considered in detail. Now, finally, another point, an important point perhaps, is that our construction here only relies on the saddle point nature of the bulk path integral. Okay, in particular, we expect our conclusions to be robust under stringy corrections. It would be interesting to check those also, that we haven't done yet. Okay, I will stop here. Thank you.
Up for his talk.
Hi, yeah, so most of your calculations were for one particular state, right? So I guess there's two questions. A, do you expect these replica symmetry things to generalize? And B, you made the statement that this is what is special about holographic states, like in general, but you flashed the computation in a particular state. So how did you?
You could make similar statements for other holographic states.
So you expect the replica symmetry stuff to actually work out? Okay, thank you.
Very quickly, and you can tell me later, maybe I missed it, but are there situations where replica symmetry must be broken? Did you?
Yeah, so this was basically, we were searching for measures that do preserve replica symmetry.
Right.
And I think there's a reason to believe that if it is not of this class, the replica symmetry will be broken. Yeah. So for example, you cannot have a junction whose labels are not in that set. So you cannot have 2, 3, 8, for example. You cannot have.
I see.
It's just topologically not possible there at the locus.
I see. So they would admit a gravitational dual, but with replica symmetry breaking.
With replica symmetry breaking. So you cannot do this final step of orbifolding. You would have to live with the fact that it's described by some higher genus surface, filled out by some handle body, and you cannot do the orbifold.
Thank you.
Okay, if there are no more questions, let's thank Abhijit again.